Okay, today we're going to look at another property of matrices. We're going to look at what's called a determinant. A determinant is a real number, a value that is associated with the matrix, a way of saying what the matrix can be represented by a single number. The basic idea is if you have a 2 by 2 matrix, then the determinant will be basically this diagonal, A11 times A22. So you multiply those two, and then you also multiply these two, the other diagonal, A21 and A12, and the difference between those two products is the determinant. It is put in lines like that to show that it is a determinant. So notice matrices have brackets while determinants have the vertical bars. Now if you're going to bigger than 2 by 2, basically what you have to do is divide up the matrix into 2 by 2 pieces, if you will. So for example, we'd start off with A11, and then it would be associated with the determinant that would be the 2 by 2 that would be in this corner. Then you could go to A12, and it would be associated with the determinant made of these two and these two. And then you could go to A13, and it would be associated with the 2 by 2 that would be in this corner. A21, A22, A31, and A32. You can do any row or column. Basically the bottom line is the 2 by 2 does not include the row or column of the element that's being associated with that 2 by 2. And we will look at some examples of how to do that shortly. But that's the bottom line, is you always pick the 4 elements that are not in the same row or same column of the value that goes out in front. The 2 by 2s are called the minor, associated with each element in that 3 by 3 matrix. We can formally represent that as Mij, and again the ij's represent the rows and columns for each one. And then the element that is associated with those is called the cofactor, and it can be labeled Aij. Now, one little easy thing to get tripped on, however, is when we do those cofactors, like when we were going across the top row here, you have to alternate the signs. And for a 3 by 3, the signs alternate this way: plus, minus, plus, and then minus, plus, minus, plus, minus, plus again. This one always starts out as a plus, and then they, in all directions, they do alternate. So plus, minus, that way. So if you had a 4 by 4, it would go plus, minus, and so forth. So in other words, that's this part here. Depending on where you are in your array, you'll have to use that positive or negative, and really, as opposed to seeing this formal general form of it, it's easier just to keep straight the plus minus pattern as you go through it. So for example, let's look at we want to evaluate this 3 by 3 here, and we're going to go across the second column. So please note, columns go this way, so the cofactors would be the -3, -4, and the 0. We like, when we're doing determinants, we like using up the zeros because, of course, that's going to be multiplied times its minor, it's 2 by 2, and since it's 0, it doesn't matter what the 2 by 2 is, that's automatically going to be 0 on that part. So, since we are starting right here, using that plus, minus, plus, we're going to have a -1 for that one, and then this one will be plus, and then that one will be back to a negative sign. So we start off with -3. There is for our signs, and then here is the 2 by 2 associated with the negative 3. So negative 1, negative 1, negative 3, and 2, that's where those come from. Then we move down, here's the negative 4, now we have a plus sign, negative plus negative, and then this one, and it has to be the 4 corners so that we're not in the row or column the negative 4 is in. So up there, over there, down there, and over here. And then finally we have the 0, back to the negative 1, minus plus minus, and then we have the things that are not again in that column or that row, so the 2, negative 1, negative 2, and negative 3. Okay, so now we can evaluate each of the minors, and again it's this diagonal subtract that diagonal, so negative 1 times 2 subtract negative 1 times negative 3. Over here it's 2 times 2 subtract the negative 1 times the negative 2, and then the last one would be 2 times the negative 3 subtract negative 1 times negative 2. So clearly one of the challenges of finding determinants is you got to keep all those signs straight. So over here we have negative 2 subtract 3, so that gives us negative 5. And so we're going to have negative 3 times negative 1 times negative 5. Here we have 4 subtract 2, so that's going to give us a 2. And then over here we have a negative 6 subtract 2 more, so that's going to give us a negative 8. So negative 3, negative 1, negative 5, a negative 15. Negative 4 times a plus 1 times a 2 gives us a negative 8. 0, so I don't really care. 0. Add that all up, and we have our answer of negative 23. Now, a couple things to note. The same result would have been achieved using any row or column of elements. So it doesn't matter where you do it. If every element in a row or column is 0, then the determinant's value is 0. If the rows of a matrix A are the corresponding columns of matrix B, then the two determinants will be equal. If any two rows of columns of matrix A are interchanged to form matrix B, then, and again, interchanged, then B will equal the negative of A. If matrix B is formed by multiplying the elements of a row or column by K, then B equals K times A. So for instance, if we were to take all of these and double them, then the overall value of the determinant would be double. If two rows of columns of matrix A are identical, then the determinant equals 0, because of course if you think back to what we were doing last time, if you subtracted one from the other, you would get a row of zeros, and therefore the whole thing would be 0. Adding to a row or column at constant times another row or column does not change the value of the determinant A, and if matrix A is a triangular form, which means only zeros above or below the diagonal, then A is simply the product of the main diagonal. So those are some rules for doing determinants. Now, this leads us to another way of solving systems of equations, and it is called Kramers Rule. And for a two equations and two unknowns case, basically the way it works is when we have a system set up like this, then the x will equal dx over d, and the y will equal dy over d. Now the d is the 2 by 2 that was made of a1, a2, b1, and b2, and that should be a b2. And then the dx is where we substitute the a1 and a2 by c1 and c2, and the dy is where we substitute b1 and b2 by c1 and c2. And so basically we find the values of those three determinants, dx, dy, and d, and those ratios will give us our values for x and y. It can also be done for three systems In other words, 3 equations and 3 unknowns. The main difference there, of course, is it's just a lot more work, but it's the same idea. So if we were to solve this 3 by 3 here, so first we're going to find the d. So that'll be made up of the coefficients that are in front of the x, y's, and z's. So 1, 2, 1, 1, 2, 1, 1, negative 1, negative 2, 1, negative 1, negative 2, negative 1, 1, 3, negative 1, 1, 3. Go ahead and find the value of the determinant, and we get that it was a negative 3, just like we were doing before. Okay, then what we're going to do is find dx, dy, and dz, and we're going to do that by replacing. So note, in the original d, it was 1, 2, 1. Well, now it's negative 2, negative 5, 4, which came from negative 2, negative 5, 4. So these replace the x values, if you will. And then we go ahead and find the value of that. That came out to be a 7 there. Did the same thing for y. Now we replace the y values. So originally the y values were 1, negative 1, 2. Now the y values are negative 2, negative 5, 4. Go ahead and find the value of that determinant. It came out negative 22. And then also the z, replacing the z values here. And that one came out to be negative 21. And then, as you can see at the bottom, the ratios, first dx over d, 7 over negative 3, that gives us the value for x. Negative 22 over 3 gave us the value of y. Since they're both negative, that's of course positive. And negative 21 over 3, negative 3 gave us the 7. So that is an example of doing Kramers Rule. So let's go ahead now and look at a few examples. We're going to evaluate these determinants. So remember, it's this diagonal, subtract that diagonal. So we're going to have negative 3 times 3, subtract negative 1 times 9. And so that'll give negative 9 plus 9, and so it equals 0. Also note, by the way, that this column was simply 3 times that one, and so if I'd have done negative 3 times this row and added it to that row, I would have had zeros. So I got zeros. Okay, over here we have 2 times 4, subtract 2 times 4, and of course that's going to be 8 subtract 8, which is 0. So when you have rows that are the same, your overall determinant value is going to be 0. So from these two examples, if 2 match, it's 0, or if one is simply a multiple, one row is simply a multiple of another, or for that matter, one column, because note that these two are just negative 3 times those two, so it can be columns as well. Those two results will give you 0 for your determinant. All right, let's look at a 3 by 3. So I'm going to pick the second column here, just because it has the 0 in the middle. Also, you know, I could have picked the second row, but I'm just picking the one with smaller numbers. Generally, less chance of mistake if I pick the ones with smaller numbers. So here we'll have first the negative 2. Okay, remember the plus, minus, plus routine. So I'm just going to go ahead and mark them so we keep them straight. So in that position we'll have a negative 1, and then that'll be times the minor, that is 7, 3, 5, and 2. Okay, so now that'll be added to the 0, which is in the +1 spot, and its one will be 8, -4, 5, and 2. And then the last one will be the -1, and that will be also times another -1 because it's in the minus plus minus position, and then the 4 for this one will be 8, -4, and 7, 3. And so now I have set up my 3 minors. Now, you might say, well, you know, I know this whole thing's going to end up 0, so why bother even doing that one? And I would just recommend laying it all out, even if you are just going to call that part 0 later on, just so that you know that you are staying in order and that you're not missing anything. All right, so let's go ahead and take care of these now. We have basically -2 times -1. This one is going to be 14. 7 times 2, subtract 15. So that's going to be a -1. And then we're going to have our 0, 1. This one is going to be 16. Subtract a -20, which makes it add. So 16 plus 20 would make it a 36. And then the last one, -1 times -1 times 24, subtract a -28, 24 plus 28, that gives me a 52. And so there we have our minors worked out. And now let's just go ahead and see 2, 1, 1, so that's just a -2. And then this will be 0. And the last part looks like it's going to be plus 52. And so the overall value of this determinant is 50. And so we have found the value of a 3 by 3 determinant. All right, we're going to look now at a case that is 4 by 4. And we have lots of zeros to choose from here. So, for example, if I were to pick this column, I've only got that one value of 6 in there. That's the only one that I would need to do because that would give me 0, that would give me 0, that would give me 0. Also considering my plus minus, that would be back to plus. So that's going to equal a 6 times a 1, and then I need the 9 elements that are not in the rows or columns of the 6. So that's going to be -2, 4, 2, then 0, 0, 3, and then 9, 2, -1. So note, you know, basically I was not picking those ones, and that gave me these. Now, the nice thing about this one is, again, I have a row here with zeros in it, so that's the only one I have to worry about because those two will give me 0, and then this is, again, plus, minus, so that's going to give me a minus when I use the 3. So this is going to equal 6 times 1, and now it's going to equal a 3 times a -1, and then its minor, -2, 4, 9, and 2. So, of course, 6 times 1, that's just going to be 6. And then inside I have the 3, -1, And then here I have negative 4, subtract 36, so that's negative 40. And so now I'm left with 6 times 3. That'll be 2 negatives, so 6 times 120. And so this will all equal 720. And I have the value of that determinant. All right, let's try a couple of examples with Kramers Rule. So here's my system. I'm going to first want to find D. D is the determinant of the coefficients in front of the x and y's. So D here is going to equal 4, 2, negative 1, and 3, which will basically be 4 times 3 subtract 2 times negative 1. And that, of course, will equal 12 plus 2, which is 14. So our D is 14. All right, now we're going to find dx, and dx is where we replace the 4 and the 2. We're going to replace the 4 and the 2 by the 0 and 14. So 0 and 14, we still have the negative 1 and 3. So that will be 0, subtract a negative 14, so that'll be 14. And then the dy, now we're going to replace the second 2 with the 0 and the 14. And here, that'll be 56, subtract 0, and so that'll be 56. Again, 4 times 14 is the 56, subtract that diagonal, which is 0. And so my x, which is dx over d, will be 14 over 14, which is 1. My y will be dy over d, which is 56 over 14, which is 4. And so my solution is 1, 4. So using Kramers Rule. And, you know, when we finally get to a quiz or test in this chapter, you know, when it says doing it by Kramers Rule, then you'll have to show it by Kramers Rule. If it says do it by a different method, then you'll have to do it by a different method. If it doesn't say, then you'll be able to choose whatever method you would like. All right, so let's look at solving a 3 by 3 now with Kramers Rule. So let's first find the determinant, our D. Let's see, we have 3, 2, 4. Wait, actually, note that's x, so that's 3, 2, 0. Here's a y, so that's 5. The middle one here doesn't have a y, so that's a 0. And here's where the 4 goes. And then the top one doesn't have a z, so that part's 0. And then it's got 7 and 3. So please note, you know, very important, you know, it's not, even though all I saw were 2 things here, x and y, x and z, y and z, and so forth, I got x, y, and z, and so I had to fit in the things that were missing. So no z in the top one, no y in the middle one, no x in the bottom one. Very important thing to make sure you keep straight. Alright, so let's see, we could do the top column first. That one's easy enough. So that's going to equal 3 times a positive 1, because remember, plus, minus, plus pattern. So that's going to, and then that's going to be times 0.743. And then we can add to that a 2, and that'll be a minus 1. And that one would be a 5.043. And then we don't have to worry about the third one. The third one's 0, and since the third one, I'll just let it go. All right, and so what are we going to have? We're going to have basically 3 for these two things, and then this is 0 minus 28. And then over here, we're going to have a negative 2, and 15 minus 0, so that'll be 15. And all together, this is going to equal a negative 114. All right, so let's go ahead and solve our dx, our dy, and our dz. And remember, we're going to be replacing first this column with negative 7, 2, negative 8, then this column for the y's with negative 7, 2, negative 8, and then the z's. So we'll start off with the dx's first. So dx, we have negative 7, 2, negative 8, 5, 0, 4, 0, 7, 3. Let's see, and we can go across the top there, and we'll have negative 7 times 1, and that'll be times, let's see, 0, 7, 4, 3, and then plus a 5 times negative 1, and then that's times a 2, 7, 2, 7, negative 8, 3, and so let's see, that will equal negative 7, this will give me negative 28, 0 minus 28, and then this will give me a negative 5 times, let's see, 6, subtract a negative 56, so that's a 62, and all of that equals a negative 114. So there is the dx. Okay, dy. dy equals, so we're back to 3, 2, 0 for the x part. And then now the negative 7 to negative 8 for the middle ones, and 0, 7, 3. And so here we'll go down that first one, since it gives us a 0 for that third one, that's good. And so 3 times 1 times 2, 7, negative 8, 3. Plus 2 times negative 1, and this is going to be negative 7, 0, negative 8, and 3. And so this one, that'll give me a 3. This part will give me a 6 minus the 56, so that's back to my 62. And then I'll have a negative 2 between those two things. And here I have negative 21 minus 0, so that's negative 21. And this one equals 228. And let's go ahead and do our DZ. And now we're going to replace the third column. So notice how those same set of numbers moved across for the X, Y, and Z. And this one, I can also go here. Again, I'm just picking one of the spots that has a 0. So that's going to be 3, 1. And this time, let's see, it's 0, 2, 4, -8. And then it has its 2 times -1. And that one's going to have 5, 4, -7, -8. And so this last one will have a 3. And then, let's see, we got 0 minus 8 plus a -2. And then this is -40 plus a 28. Yeah, because see, -40. And then subtract a -28, so that becomes plus a 28, so that'll be a -12. And let's see, that's -24 plus 24, so that one is 0. Alright, so the x part is dx over d. Dx was -114. The d was -114, so that is 1. The y is dy over d. So that is 228 over -114, which is -2. And then the z is dz over d, which is 0 over -114. And of course that's 0. And so our answer is 1, -2, 0. And there you have section 5.3.